Hi everybody! It's the last day of Chem 161. Which is why I'm subjecting you to this music forever until you ask me questions. It was about to loop, like, it only goes for 15 minutes. I wanted to get this on the screen. Boop. Boop. I turned it off on accident. Apparently, if I hit the spacebar, it does this all day. Doot, 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 doot. There we go. All right, so here is the thing from the slide. I can't actually draw on this, so I can minimize it and get it out of the way. And we'll get, oops. We'll do that. So now I could just hide this and draw stuff over. Or I could just move this to the side, I guess. That doesn't really give me much space to work with, I suppose. But so, if you recall from when we talked about molecular geometry, so determining the VSEPR geometry is just counting the number of electron domains. So that's the wrong thing. I didn't have anything to capture either. Hold on just a second here. Okay. So, if you have, let's see here. So if you count the number of electron groups around your central atom. So I'm going to just draw a generic central atom. And then I'm going to connect 2 electron domains to it. So with 2, I get linear. With 3, I get trigonal planar. And we'll write out all the shapes here. Now, why do these specific shapes form? This is because, not H. This is because that's the basis behind VSEPRs, that electrons will repel as far apart as they possibly can. They want to maximize the bond angle between themselves and their adjacent electron pairs that they are nearby. I'm going to take a sip of water there. So 4 is, whoop, we'll draw this. And I'm going to try and draw like this little planar triangle here to help it look like that. Ah, jeez. Steve messaged me and it scared the crap out of me. All right, so let me just turn that volume down. And then the last one's octahedral. All right, so that's the VSEPR geometry, or electron pair geometry. I forget which one your book calls it. I wish that books would give this the same name, but whatever. And really, all you have to do here is you just have to count the number of electron groups. Remember that an electron group can be Any number of bonds to another atom. So a single bond, a double bond, or a triple bond, each of those is one electron group. Or a non-bonding electron pair. And it's where we have the non-bonding electron pairs where things get interesting. And that's where this chart comes in, this thing right here. So if I move this over, it'll be absolutely worthless because it doesn't fit. Never mind. But I guess I could just kind of crop all of this out here. So let me make this like that. There we go. And then I have to cover the chat up for a little bit here, but okay. Those more or less line up. So, okay. On the left, we have the electron group geometry or electron pair geometry. I call it the Vesper geometry. That's just the family that the molecule belongs to. Now, if you have no electron pairs, then all of the atoms that are bonded to the central atom are going to be in those little spaces where these circles are. So, for example, if I had something that had 3 electron groups, its Vesper geometry would be trigonal planar. But if none of those were electron pairs, its molecular shape would also be trigonal planar. If one of them was an electron pair, it would be bent. And we're getting that just off the chart here. This right here. So if I have 0, this is where I'm at. If I have 1, this is where I'm at. So going down to tetrahedral here, tetrahedral is for 4 electron groups. If none of them are electron pairs, the molecular shape is tetrahedral. If one of them is an electron pair, we call it trigonal pyramidal. And if 2 of them are electron pairs, we call it bent. So you basically just apply the chart to which one of these you are in. So which of the groups. I didn't mean to go through everything there. So this will be your Vesper or electron geometry. Which one of those categories are you in? 2, 3, 4, 5, or 6? And then you go over to the chart for whichever category you're in. You then just look at this chart here and say, okay, of those 6 groups or of those 3 groups or whatever, how many electron pairs do I have around the central atom? And then you choose the correct member. Number 5, when it says show your work in that graph, as long as you're in that blue region, you're good. Sorry, not graph, but I mean just like show what you did. You just have to put it in that box. And you can use that box however you see fit. However, I would prefer that if you are going to work and show calculations or stuff, so if this is your box, please work in this manner. So like start in the top left and go to the top, or start top left and then write like you're writing a paragraph or something like that. Like it doesn't have to be perfect, obviously, but if your calculations are like say, so like here's number 1 and then here's number 2 and then here's number 3 and then here's number 4 and then here's number 5. Like if I have to connect the dots like that, I might not make the connection that you want me to, or I may not even be able to see a connection because I'll be looking logically, just trying to go left to right, and they'll be like, well, why are we way over here? So don't just cram it in wherever there's space. Do organize it a little bit. And that'll be okay. Remember, part of the assignment is really just, can you communicate your thoughts on the topic to me? And if you presented this, I would say that not effectively, because we don't typically interpret information in this manner. This would be much more concise. So 1, 2. Because this is what English this is how English is written. Left to right, top to bottom. Like if this was an Arabic class, I would expect you to go right to left, top to bottom. Or if this was Japanese, we would go top to bottom, left to right. So we do have to conform to the standards of our language that we are using. But that's really the only requirement. Anything else, let me know. Because I'm just going to put the music back on. So here we go. And I'll just hang out here for a bit until there's more questions. Do, do, do. Do, do, do. Yeah, the final is graded exactly the same way. So it's out of 165, but I only count 150 points. So there's 15 extra credit points if you get a perfect score. The trade-off is that the final is very long. That's something I should do, actually. Hold on, let me do this real quick. I should tell you what the statistics of the final are. Not like what people have got on it, because you haven't taken the final yet. But like, how many questions is it, etc. So we'll go boop, boop. All right, so let me get this out. So final exam. And let me put this information over here. All right, so I wish this was a typo, but there are 73 questions. And let's see here. Time limit. I gave you 150 minutes, which is 2.5 hours. And you can take it twice. And then, when is the final open? I have to actually do this so I can see that. So it opens at midnight tonight on the 17th, which is Wednesday. And it closes at 11:59 p.m. on Thursday. So you have 2 days to do the final. You can take it once on Wednesday and once on Thursday. You can take it both times on Thursday. You can take it both times on Wednesday. It doesn't matter to me. But I realize with finals week, like, I don't want to make it so that you take it only one time during this 2.5 hour specific window during the middle of the week. Because some of y'all work, obviously. I'm not going to assume that of the 30 people in my class, 0 of them work. Like, that's not a realistic assumption. So any time that I choose would be a conflict. So I give you all day. Do it whenever you want to, as long as you do it. We have enough shit to do during the pandemic. When the pandemic is over, then I'll go back to being a hard ass, but I'm not really a hard ass. People just think I am. No problem, you got it. Alright. What else? Let me know. Otherwise, I'm just gonna torment you with more of this again, so. I'm actually sitting here rocking in my chair. I don't know why, but this stupid little song is so good. Finals on everything for the quarter. The entire very first day all the way to last Wednesday, which was the last day we had class. Yeah, we can go over those. There you go. Every time I wind down the music for you guys, I have to stop it manually for me because I still hear it. What did I click on? Oops. On live chat. I accidentally clicked something, so I don't want this message. Oh well, whatever. Okay, so how do you get the equation for the trend line that you constructed from the table? So, do you mean like what do you click on in Google Sheets? I'm gonna have to find that, so give me a second here. Because you should be able to like format trendline and then add a label to it. Let me see if I can find that. So we definitely did that in the... Which lab? Probably lab number 2. But I will find that faster than it will take to go through that video. So let me see here. I will just open lab worksheet number 5 here. Give me just a second here. So I'm gonna play around with it. So let me just. Oh, you got it? Okay, cool. Let me just make a graph real quick. Oh, who uses a bar graph? Seriously. There we go. There you go. Yeah. So you use let me capture that actually real quick. I don't know where this is going to be centered. Oh, look at that. That's perfect. Okay. So when you go into here, so you go into the chart editor. So initially, this is what it looked like. Like, who the hell uses? What sort of graph is this? Like, if you're an economist or something. So go down to scatter because that's really the only useful graph in science is a scatter plot. And then you go over here to customize trend line. So it'll put your line in there, and then scroll down, and it'll ask you for a label, and you want to use the equation. And then I show R squared in there. I made a line that was literally 1. So there's my equation. Now, how do you interpret the equation? So let's see here. So let me get rid of this. So if your equation on the graph is plotting absorbance versus concentration, and the concentration is in percent ethanol, and this is your graph or something like that. Actually, you know what? Let me just do a different color. There you go. And this is your graph. Then remember that the equation for Beer's law is this. And that L is just the path length. So effectively, your equation just becomes this. So if you want to look at your graph, well, if A is the y-axis and C is the x-axis, this must be the slope, right? Now, the units of the slope will be slightly different. They will be in... They're whatever this cancels out with C so that A has no units. Because remember, absorbance is a dimensionless quantity. So the units here would be, well, if L is path length, that would be inverse centimeters times inverse percent, which is a really stupid unit, but that's the units that we're using. So so you should get an equation. If your equation has a y-intercept, that's error. Because a 0 concentration should have a 0 absorbance, right? So you can effectively ignore that when trying to determine concentrations, but just do the algebra. So, like, subtract whatever amount your plus term is, or add whatever amount if it's a negative. And then you could solve for A or C as needed. But epsilon will just appear on your graph immediately, because if your graph says something like, oh, your equation was y equals 3,842 x plus 0.038, well, there's your epsilons right there. Because this right here is this right here. And then again, this is 1, so we ignore it right here. One of the skills that we try and instill in you, in not just really this class, but as you go through chemistry, and then eventually when you go through physics, depending on what your major is that you're going to be graphing a lot of data. And you can make a line out of anything. So the whole point of making a graph is to try and make it into a line somehow. So this equation is super important in science. And then really that's just realizing like, oh, okay. Well, this is just whatever my... What are my cats doing? What are you doing? I think she jumped out of the laundry hamper and it almost fell over on top of her. Maya wants to say bye to you guys, by the way. Here, I'll put her on. Maya, come back. Oh, she ran away. Maya! She'll be back, whatever. So, the Y is, in this case, would be whatever is on your Y-axis. This would be whatever's on your X-axis. And then this is just your slope and Y-intercept, right? So try and match the equations that we give you to y equals mx plus b whenever you can if graphing is involved. And then this will become a lot simpler because you just match them up one for one. I was telling another student the other day that in 162, we give you a different equation that's like natural log of p versus 1 over t. And the equations get ridiculous. Like, what the hell? How do you make this an equation? But you can also manipulate your axes and do other things to them just to turn everything into lines. And then the slope for the line will be whatever the slope of the equation is. So that's a super useful skill to have. And you'll pick that up more and more as you go on. I realize this is like the third time that we've done this. We don't really do enough graphs in chemistry, I feel. But this isn't really a lab-only class, so like if we were making you do an experiment every week and then working up the data, I would just make you do graphs all the time. You're like, here, make a graph. Show me your graph. All right. Other question was calculating wavelength. So, I need to hit clear again. Boop. And so for wavelength, you have two formulas, really. So E equals hc over lambda, which is the same as h times frequency. Or you have c equals lambda times frequency. And so wavelength's always going to be in meters. I just realized you might care more about the Rydberg equation. So you also have this equation, which is RH. Sorry, I'm HCRH. I'm thinking of the one that's way too complicated. So n squared over n squared. I think it's this. Smaller number. Bigger. Yeah, that's right. Okay. I don't ever remember the positions of the final minus initial because I always just make this be a positive number. So, I'm not sure which equation you wanted. I'm assuming it's this one, now that I think about it, but if it's not, let me know. And I could do any of these equations. I could just make whatever problem you want me to. Okay, so let's do an example here. So I'm going to pick... So let's make a nucleus here. So here's the nucleus. And we'll say... my electron absorbs energy and it ends up here. Whee! And then it hops down to... I don't know, let's just go 5 to 1. We'll go all the way back down to the beginning. So I want to go from 5 to 1. So calculate the wavelength of that. So let's do that. So So this would be n initial, and this would be n final. So I would say inverse wavelength is equal to the Rydberg constant times whatever n final. I'm just rewriting the equation. I don't need to do that. So RH is... Oh, I never get this number right. I think that that's right. Let me go look it up. Google says 10973,731, which might be a little more specific than I actually have. Let me just see what I have in the slides here. Where's Unit 3? Rydberg. They may have updated it ever since I wrote these slides, because these constants do get updated, believe it or not. 1096776. Is that what I have? Yeah, okay. We'll just use that because that's in the notes. Times 1 over n final squared. So n final was 1, so that's just 1 squared. Minus 1 over n initial squared, which is 5 squared. So you could just punch this into your calculator, but the result of that subtraction should be this. And then when I multiply these two things together, I get the inverse of wavelength equals some number of inverse meters. And so where's my calculator? 1096776 times 10 to the 7 times 24 divided by 25. And I get 1, 2, 3, 4, 5, 6, 7 is what I get for my answer. Now, obviously, that's not a wavelength. That's an inverse wavelength. So now what I want to do is I want to do this. I'm going to take the inverse of it. So all you have to do is take the number that's currently in your calculator screen and hit the inverse button. Answer to the -1. And what an inverse does is it just does 1 over everything, right? Well, 1 over something is just that something. So this then becomes lambda, which will be in meters now. And this is 9.497533 times 10 to the -8 meters. Or 94.97533 nanometers. So the wavelength for the transition from n equals 5 to n equals 1 is about 95 nanometers, which we would actually say, oh, that's probably in the UV region. And it totally is. And then what we can do... So I can just check the answer here. It's not the Balmer series, though. What is this called? Is this the Lyman series? Yeah, there we go. And they don't have that one on the picture, so I can't check that, but I bet they have a table. So the wavelength for 5 to 1, according to Wikipedia, is 94.974,287. So that's really close, but if you just went to Google and typed in that number, you get the wrong answer. Because Canvas would be like, oh, you're outside of the bounds of the error. Because you didn't use the correct Rydberg constant. Use the Rydberg constant in your notes. So you could check your answer on Wikipedia. That's going to use up some time, but just be mindful of that. So that's the gist of how to do that type of problem. Is you just plug in the numbers into n, get the inverse wavelength, and then take the inverse of the result, and then turn it into nanometers. This result right here that I'm going to box in pink here, or whatever this color is. This always has to be a positive number. Because if it's negative, you're going to get a negative wavelength. So if you get a negative number, swap the positions of these two. Because you'll get the same number, but it'll be positive. And we can show that down here. So like if I had 3 minus 5, you get this, right? But if I just swap the position of the two numbers, now I get the positive result of it. Because you're just subtracting, your result is subtraction around the origin. So you're going to appear on the around the origin the same distance, just on the opposite side if you subtract the terms in a different order. So if you're plugging in numbers, or if you're like, oh, I don't remember if it's NI or NF or whatever, just throw in the numbers however you want to, and then get rid of the negative sign. And it's fine. It totally works, because that's how math works. That's what I do. I just plug in the numbers in whatever order I think to. And then I get the answer, and then if I get a negative number, I just turn it positive, because that's the same as me going back and doing the calculation again and reversing the numbers. Now, I should be clear that if you are trying to just play fast and loose with negative signs, this really only works with lambda. So if you're solving for a wavelength always needs to be positive. If you're solving for energy, which is something that you could do with an equation really similar to this, the sign does matter on energy, but you can then rationalize that by saying, oh, do I want the energy of the photon emitted or the energy of the atom afterward? Well, the energy of the photon has to be a positive number, because you can't have negative energy in a photon. And the energy of the atom should be negative, because the process in which you are emitting a photon is exothermic. Energy is going out of the system. So you can play around with the signs there, but then the signs actually matter depending on the context. So be context aware of the problems that you're doing. All right. Other questions, let me know. Alright, last call for questions. Let me know if you have anything to ask in the chat. Alright, doesn't seem like there's any more questions, so I guess we're gonna just wind this down here. And we'll leave it at that. So, like we said earlier in the program, not a TV host, what am I saying? Like we said earlier in the review session, the final exam will open tonight midnight. Obviously, don't just hop in there at 12:01. Like, get a good night's rest. Study a little more if you need to. Relax, you're going to do okay. You take the final twice. Grades will be posted by next Monday for everything. And then your grades will show up on the transcript shortly after that. So, again, thanks for everything. And I hope that you found this all to be informative and useful this entire quarter. Good luck in 162.